Hello, everybody. I hope you can hear and see me. If anyone cannot see me or hear, please write it in on the chat. So, thank you all for making the time. Let's wait a couple of minutes as people seem to be joining, and we'll start in 2 minutes. Okay, we're starting in 1 minute. Okay, as you can see, we're already 45 people. I think that's great. So we're ready to start. Okay, so again, hello to everyone from Amsterdam. Here is already afternoon. Thank you very much for joining this session. My name is Panos Alexopoulos, and this is going to be my masterclass on automatic quality assessment of knowledge graphs. In case you haven't met me before, I'm a practitioner in the area of semantic technologies and ontologies since around 2006, both in a research and a practitioner capacity. And for the last 7 years, I've been working as head of ontology at TextKernel. TextKernel is a company that develops software, semantic software for analyzing jobs and CVs and matching them together. And my role within this company is to develop and deliver a large knowledge graph related to the HR and recruitment domain. And around 3 years ago, I published a book on good practices, good and bad practices actually, on how to build knowledge graphs and general semantic models. And this tutorial is largely based on this book. So, what are we going to talk about today? Of course, the protagonist here is knowledge graphs, right? My assumption is that at least the majority of you knows already what a knowledge graph is, or at least you have interacted with a knowledge graph either as a developer or as a user. But I would like to offer also my shot on a definition on what a knowledge graph is. So, in my view, a knowledge graph is an artifact that consists of entities that are either connected to each other, that they are related to each other under explicit and shared semantics. In that sense, it's not really something really new. It's not really a new concept, but rather a rebranding of terms like semantic networks, knowledge bases, ontologies, linked data, and many other similar terminologies that we have seen since the 80s and the 90s. And even if you haven't really worked with knowledge graphs, but you have worked with generally data models or with database schemas, taxonomies, ontologies, or other types of structured data, then you already know a lot about knowledge graphs. What, however, you may have missed, and it's something that I think it's important to stress about knowledge graphs and generally about semantic models, is the shared semantics aspect. So practically, when we talk about knowledge graphs, right, we can start discussing about their technology stack, right? If we are using RDF and semantic web technologies in general to represent them, if we use property graphs like Neo4j, for example, if we use NoSQL databases, JSON, linked data, and other representation technologies. We can talk about size and connectivity. We can talk about graphs that are that have millions and billions of entities and many relations and very rich semantics, as opposed to small knowledge graphs. Their scope can be in a single domain or multiple domains, and also their purpose can be multiple, right? There are knowledge graphs that are used mainly for data analytics, knowledge graphs that are used for data integration, for semantic search, for question answering, and lately even for enhancing AI applications, especially with respect to machine learning, using knowledge graph as a way to inject structured knowledge into these systems, plus making them more explainable and more transparent. However, as I said, these are important dimensions, but not so much defining. What, in my view, is crucial for a knowledge graph is to have three things. Is to have accuracy of meaning. That is, the meaning of every assertion in the knowledge graph should be accurate for all people and systems that use the graph. The second thing is that the meaning of the graph should be, the meaning of the elements of the graph should be explicit. That is, that any person, an individual human, individual person or system that uses the graph can understand what its entity, relation, or other element is about. What does it mean, right? Without needing to resort to external documentation or to some other resource. And the third dimension is meaning agreement, right? How commonly acceptable is the meaning of its entity, relation, or other element of the graph among people and systems that use it. In that sense, I want to talk today about knowledge graph quality, and that is how do we practically ensure that these three requirements, these three dimensions, are covered. So today's masterclass will consist of three parts. First, we're going to talk about dimensions, quality dimensions. That is, what quality aspects should we care about when developing and applying knowledge graphs. Second, we will see what can go wrong in each of these quality dimensions and why. What are the typical problems that we face as when we develop knowledge graphs, and what are some high-level reasons that these things happen. And the third aspect is what are some ways to detect quality problems in an as much as possible automatic way. I put here semi-automatic way, but what I'm going to demonstrate is some very easy ways that we can use NLP and other types of tools to detect problems in a knowledge graph, even if we have never seen this graph before, even if it's just a new graph. So the agenda is simple. The first session, I'm going to present and discuss about the quality dimensions and the problem causes of knowledge graphs. The second session will be about a particular problem that we often see in knowledge graph, and this is about bad synonymy. That is, entities that are look synonymous, but they really are not, and vice versa. Entities that should be synonyms, that should be under the same entity, but they are different. And the third session is going to be about detecting bad classes. I will explain two ways that our class definition in a knowledge graph and in an ontology can be problematic, and I will demonstrate a couple of ways to early detect those problematic classes. In this masterclass, I'm going to utilize three main detection technologies, ranging from very simple, very naive to more sophisticated. So, and the knowledge graph that we're going to examine and we're going to assess its to try to detect within it quality problems is KBpedia. Some background. Space is a generic NLP library that allows to take sentences, tokenize them, make perform entity extraction, perform relation extraction, perform dependency parsing, and other types of low-level or higher-level NLP tasks. SBERT, or also called sentence transformers, is a framework, is a deep learning model that learns embeddings about terms and sentences and allows us to detect semantic similarity between them. It's going to be a useful tool for what we're going to see. And the third tool, most likely GPT-3 system, which is a generative large language model. And the reason I picked these three is exactly because, as I said, they are from the very simple to the more sophisticated ones. And what I'm going to illustrate is that even with simple tools, we can detect quite easily some of the typical problems that happen in knowledge graphs. Now, for this masterclass, I have created a Google folder, which I'm going to share with you right now. I will stop sharing, and I will show you. So I'm putting in the chat the link of a Google folder. Please, you should all have access as a viewer. Let me know if someone has a problem accessing it. And what this contains is this. Let me show you. So this folder contains three things. One is the slides that I'm using. You can take them with you after this masterclass, or you can just follow it if you want. A Jupyter notebook that I'm going to use for the hands-on exercises, and the KBpedia knowledge graph that we are going to use for demonstrating the techniques that we're going to learn. So let me see. Excuse me for a moment. Okay, so I hope you're able to check, to have access on that. So something that I would like to do as a preparation is, please download this, the N3, download this, the file that contains our knowledge graph, and then follow me, and then please open the Jupyter notebook. So let me check, sorry. So download again the knowledge graph, and please go to the Jupyter notebook. And why is that? Because what we're going to do before we even start discussing is we need to upload in the Colab notebook the model. So in order to do that, go here in upload to session storage and make sure that the KBpedia reference concepts N3 is loaded. This is a preparation, and as you do that, I will continue with the presentation, and then we will revisit this notebook when we start the hands-on part. Okay, so moving on. Okay, so let's talk about the quality dimensions and the typical problems that we see in this dimension. The first and foremost dimension is semantic accuracy. When we have a semantic model, when we have a knowledge graph, the question of accuracy is what is the degree to which every semantic assertion of a model are accepted to be true, right? So if, for example, you have a knowledge graph that says that Panos Alexopoulos works for, I don't know, Google, that's obviously wrong, right? It's a wrong statement, which means that it isn't correct, and therefore it lowers down the accuracy of the graph. And The question is, and I have an example here actually. This is from a knowledge graph called ESCO. ESCO is a knowledge graph that relates professions, occupations actually to skills. And this is the relation between occupations and the skills that are essential for this occupation, right? So I haven't really visualized it as a graph here, but you can imagine that we have nodes about occupation, data scientist, knowledge engineer, data entry supervisor, and then nodes about each skill. And there is a relation between occupation and skills, and the relation is called is essential skill of. Now, let's try and think why. Please contemplate this content and think about how would you assess the semantic accuracy of this knowledge and what it would that be, right? So practically here we need to decide as humans whether every pair of an occupation and essential skill is correct or not. So, for example, if you are a knowledge engineer, is it essential to know about business intelligence? Is it essential to know about task algorithmization, web programming, etc., etc.? Right. So the typical way that we would check the accuracy would be to have some annotator, some human expert to decide if something is correct or not, and then calculate the ratio between correct statements and total statements. That would be the accuracy. Now, why a knowledge graph may be inaccurate, right? Why may it contain false statements? One reason has to do with knowledge graphs that are populated and constructed automatically, right? Where we use automatic information extraction methods, either from text or from other structured resources. When these methods themselves are inaccurate and they contain some form of, some degree of imprecision, this imprecision, of course, passes to the knowledge graph. It may also be that the method itself is good, is correct, but the data source from which assertions are extracted is wrong, right? So if you are creating a knowledge graph from, for example, a database that contains already wrong statements, then these wrong statements will appear also in the knowledge graph. If you are reading the assertions of the knowledge graph from articles, and these articles happen to contain misinformation and wrong statements, then these wrong statements will also appear in the knowledge graph. A third reason is when we misunderstand modeling elements, the semantics and intended usage. So, for example, and as I will show later, there is a very frequent misconception about what a subclass is between two classes in an ontology and a knowledge graph. And many times the subclass relation, instead of representing really this relation, actually represents other relations like part of, like part of relation or just relatedness. Of course, there's also the case that we have lack of domain knowledge and expertise, biases that can happen, and vagueness. I'd like to talk a bit more about vagueness. So vagueness is a semantic phenomenon where we have predicates that admit borderline cases. That is, cases where it is not determinately true that the predicate applies or not. You will recognize vagueness when you have terms like large, near, average, tall, strategic, poor, old, and these kind of things. So what's the problem with that? Vagueness causes disagreements. So as you can see here in this fictional dialogue, right? Imagine that you are defining in your knowledge graph the concept of the class of strategic client, which means that the instances of that are clients that have a strategic importance. And you also have the concept of large budget project, right? Where you use it to classify projects that have, as you say, a large budget. And you see disagreement here from the other person that an exact amount of 300,000 is not a large budget. So the question is, what is a large budget? What's the exact range of large? If it is not well defined, then the concept is vague. The term large is vague, and therefore it is subject to interpretation. It can be context dependent, it can be subjective, and therefore it can cause disagreements. And generally, when you have vagueness in your knowledge graph, in the classes or in relations, this can cause problems in at least three different use cases. One is when you use the vague data to do analytics or to use it in your application, when you reuse vague data, or when you integrate from different sources, because then you might have very different semantics and very different interpretation of the seemingly same information. So give me one moment because I got some requests about sharing the Google Drive. And I will start again. So yeah, keep in mind that I'm not able to share this as editor, so please create for the notebook, if you want to run it yourselves, please create a copy. Okay. And also, if you have any questions for the Q&A, please put them under the Q&A field not in the chat. Just put that under the Q&A. So let me continue with the presentation. Okay. So after accuracy, before. So I was talking about the problematic scenario. So imagine, as I said, that we have all this. So based on that, why would you think that we have not so good, not perfect accuracy in the following knowledge, right? Because, for instance, when I see here, I cannot think that I don't agree, at least, that for a knowledge engineer needs really to know web programming, right, or to know about perhaps algorithmization, right? At least it's not essential, right? And also it's not necessarily essential to know about RDF, because we don't really build only ontologies with RDF. But let's say that's debatable. But you can already see that the main problem here that appears is that the term essential is vague. There are no crisp criteria of essentiality that allows to unilaterally agree that a skill is essential or not. There's a lot of subjectivity. There's also a lot of context dependence, right? A knowledge engineer that will work in a semantic web project really needs to know RDF, right? A knowledge engineer that works with a different framework does not necessarily need to know RDF. Okay, let's move now to another dimension called completeness. Completeness is the degree to which elements that should be contained in the model are indeed there, right? So, in other words, does the knowledge graph contain all the relevant and necessary knowledge of the domain or of the application that it's supposed to support? Again, here you see that we have some essential skill. I bet that, again, if I make a poll here and ask you about some additional essential skills, you will probably have some ideas on what additional skills a person needs to have, right? So these are just some examples. So in that sense, the completeness is not 100%. Now, why is that? A knowledge graph generally may be incomplete when it tries to cover a very large domain and a very complex domain, and therefore it's very hard to really develop it fast enough so that it covers all the domain fast enough. So in the majority of the cases, knowledge graphs are incomplete, right? It's not very realistic to expect that any given knowledge graph has the complete knowledge of the domain it's supposed to cover. Also, in some other cases, it's the knowledge graph may be incomplete because we don't have available automatic construction methods and tools, meaning that we need to do it mainly manual, and that, of course, takes a lot of time, takes a lot of effort, takes a lot of money. It's also possible that we don't have appropriate data sources from which to derive the knowledge graph. Vagueness can play a role, and most importantly, domain volatility and dynamics, right? Because if we are building a knowledge graph whose domain keeps changing, right? Changing in the sense that we tend to get a new knowledge very frequently and existing knowledge becomes obsolete very frequently, and then in order to catch up, right, we need to have a very efficient population methodology for the knowledge graph. Okay, then we have consistency. Consistency is more of a logical construct, and it has to do with the degree to which a semantic model is free of logical or semantic contradictions. Um, yeah. So, for example, you cannot have a graph that says at the same time that I don't know, Panos was born in Greece and Panos was born in the United States when Panos is the same person, because a person cannot be born in more than one locations, right? Now, why knowledge graph may be inconsistent? Usually, this is why this happens is because we really don't have or don't enforce appropriate constraints and consistency rules. Either we're too lazy, well, it's a big word, but yeah, or we're too busy to create such constraints, or sometimes the modeling framework that we employ does not inherently support it, or that the enforcement of such rules can be computationally too complex, especially as you have a very large knowledge graph. Then we go to conciseness. Conciseness is the degree to which the model does not contain redundant elements. Redundant elements are elements like concepts, entities, or relations, or other that represent the same thing but in a different construct, right? So, for example, imagine that you have a concept of you are modeling in your knowledge graph films, right? And you want to represent the directors of the films, right? If you define both a relation has director and an attribute director, then that's redundancy, because you don't really need to both a relation and an attribute to represent the same information, right? Sometimes it may be needed, but generally conciseness is about having only the knowledge that you need. So the reason why a knowledge graph may be inconcise, one main reason is that we have uncoordinated modeling from multiple parties with inadequate governance. So usually the problem of inconciseness comes when we have distributed knowledge graph development from multiple parties. It can also happen when we try to optimize for different applications at the same time, and that means that it can be that one application requires one particular way to represent a piece of information, and another application maybe require a different way to represent the same piece of information. And in that sense, you really need the redundancy. It can also happen that sometimes we do hacks or we add temporary elements that we haven't removed, and also we leave legacy elements that we also haven't removed. Another important dimension is timeliness. Timeliness is the degree to which the model contains elements that reflect the current version of the world, right? So, for example, again, if we take this piece of knowledge here, this relation was created around now I think 7 years ago. This is actually 7 years old, right? So even if, let's say, 7 years old, even if we assume that this information was correct, right, was being accurate, it's not necessary that it still is. It may be that, for example, one of these technologies here does not exist anymore, or nobody uses it anymore, which means that it's not essential anymore, right? Or it may be that a knowledge engineer now, because needs to also know more advanced NLP, like or language models like GPT-3 or other types of skills, right? So in that sense, you can have a perfectly correct, let's say, knowledge graph for when it was developed, but then it's not timely anymore. The knowledge it contains is not relevant anymore, it's not correct anymore. And why this may happen? Well, this usually happens when the domain is highly volatile and changes very often, and the model maintenance and evolution mechanisms that we have in place are not able to detect and incorporate these changes, right? So it's about how fast can we monitor and follow up on the evolution of the domain and the knowledge graph. Relevancy. Relevancy is the degree to which the model structure and content are useful and important for a given task or application, right? Apart from few cases, almost always the knowledge graph, the reason we build a knowledge graph is to power some application. This can be data analytics application, it can be an AI application, a machine learning model, doesn't matter. And you can have a perfect knowledge graph when you see it from an objective perspective, but when it comes to being actually useful for the application that you want it, does not meet all the requirements, both in terms of representation, in terms of content, or some other dimension. It's want knowledge graph to meet the applications for which it has been developed, right? And why it may be relevant? Well, first, it might contain relevant information about the domain, but misses information that is critical for the task. Or that it's relevant, it contains the relevant information, but it's not easily accessible, or it has been developed without having considered the application requirements, which of course can happen. And that's why usually it's a good practice when we build a knowledge graph for an application, we really need to consider what the application is about. Another dimension, which I think is also very important, is understandability. Understandability is about humans, is the ease with which human consumers can understand and utilize the knowledge graph elements without misunderstanding or doubting their meaning. So it's not about machine semantics, it's about human semantics. So if I tell you, for example, that I have a class in my knowledge graph called, I don't know, profession, right? Yes, you probably understand what profession is about. But if I give you some other very specific, very niche concept that you may not know what this is about, if my class is not accompanied by a proper definition, by additional information that will help you understand what it is about, then the understandability of the graph will be low. And why a knowledge graph may be difficult to understand? Usually it comes from bad or inadequate descriptions. The names themselves of the entities can be ambiguous or inaccurate. We may have obscure axioms. We may lack human readable definitions. And it can also be that many assumptions and biases are not documented, right? Which happens everywhere, but it also happens in knowledge graphs. And last thing is trustworthiness, right? Ultimately, we want whatever we build, the knowledge graphs that we build, to be trustworthy. Trustworthiness is related to all the previous dimensions that I mentioned, but ultimately it's about the perception and confidence that the knowledge graph has the quality that as a user I want and I need, right? It's not about having necessarily the perfect quality, but it needs to be consistent, it needs to be transparent as to what its quality is, right? So in that sense, trustworthiness is not a simple metric to calculate. And it's not, you can have a knowledge graph with, let's say, 95% accuracy, but if that 5% that is wrong has embarrassing errors or has really dangerous errors, right, then the knowledge graph will not be trustworthy. So generally, a knowledge graph may be untrustworthy if it's not really adopted or endorsed by different communities and industries. If you have no information about its content, about its quality, about its evaluation and experience reports, if it doesn't have provenance, and generally if you have reasons to believe that the model contains biases and reflects the own interest of its creators. So for instance, here, we saw that there are, because of the vagueness of the relation of essentiality between occupations and skills, right, we can have disagreements. And one question to pose is, whoever built this, what biases could they have, right? Because if you think that some domain expert decided that the knowledge engineer needs to know web programming, why that might have happened? It may have happened because that particular domain expert was working in a very context-specific environment where knowledge engineers perhaps did web programming, and therefore they were biased. The domain experts were biased towards incorporating that, right? But the thing is that if you go to this model, you will realize that there's not such information there. We really don't know the provenance of the domain experts that created this knowledge graph. Who decided how many, what processes they follow, right? Okay, time for some first Q&A. So let me know if you have any questions so far. I stopped sharing my screen. Nice that you're already 70 people. So is there any question? Please add it in the Q&A. Or in the chat if you want. I don't know, but better in the Q&A session. Okay, let me pose a question, and please add this into the chat. Is there okay, let's have a question. How can we prevent knowledge graph decrease in accuracy at the business level? That's a great question. So decreasing accuracy, right? If you think about it based on the definition, the accuracy will decrease if the new knowledge that is added in the knowledge graph contains more errors than before, right? So if you start with an initial knowledge graph that has 90% accuracy and 3 months later it has 60%, it means that it has that you have added noise, you have added wrong information, right? So preventing is about having very well defined and as much as high quality processes for maintaining the graph, right? Which means that if, let's say, you make a great effort to build a very accurate knowledge graph in the beginning, right? But still you need to have a maintenance process later, so that actually after 1 year later, for example, the accuracy hasn't decreased. Now, the exact methods to do that have to do with how exactly you maintain the graph. So, for instance, if you are going to maintain the graph mostly manual with annotators, with domain experts, or with a team that does that, with humans in general, you need to perform a good training to these people about semantics and about what it should contain. If you use machine learning, NLP, and other methods, automatic methods to extract, then you need to monitor, to keep monitoring the quality of the extraction process and perhaps the quality of the data sources that you use, right? So it really has to do with the maintenance process. You need the maintenance and evolution process of the knowledge graph needs to be high quality so that you don't prevent not only accuracy but all the other dimensions as well to decay. There's a question here. I can see. I'm sorry if I missed it, but what is the standard measure of accuracy for knowledge graph? I mean, you can use the. You mean metric or a particular? Because I see you say 5%. You mean what is the actual accuracy, or what metric do we use for a knowledge graph? Can you, Victoria? Can you clarify this? So I can answer it. So as a metric, as I said, the typical metric, the easiest metric is to take a sample of the knowledge graph, assertions, and note down which are correct and which are not correct, and then take the ratio of correct to the total. Right now, different knowledge graphs, different knowledge graphs have different tolerance and different levels of accuracy, and it has to do with a lot of factors. Yeah, the metric, I think I answered that. Another question about tools. Yeah, I think this is a question for the end. I will show already some tools and techniques, very easy, and we can discuss further for additional tools. There's another question. Can we explicitly label confidence on insertion and give some sense of timelines with some decay measure, like we expect these relations to be correct for 1 week? I guess you could. It would be. It's an interesting. It's an interesting idea. We need to see how it's going to be implemented. But yeah, definitely something that can be useful is to say this assertion that I added, this statement that I added in my knowledge graph. I have this confidence that it is correct based on the way that I have acquired it, based on like a prior probability that this assertion is correct. It's actually a good practice to include that. Okay, so I'd like to move on with my presentation and start the second part, which is about okay. Now I'm going to talk now about bad synonyms. So this is a particular quality problem that I have experienced in many knowledge graphs that I have used or reused for the past years. And it has to do with the famous labels of entities and relations. So again, I assume that most of you are aware of the so-called labels in RDF. I use the term lexicalization here, and what lexicalization is for an entity is that because in a knowledge graph and in ontologies in general, we represent things, not strings, right? And we use entities. We need a way, typically, to know how a particular entity may be expressed in natural language. In natural language, and this comes from lexicalization or otherwise labels, right? So, for example, you have here the entity shrubs, and you can see that it has a main name called shrubs, and then it has alternative labels, as they are called, in different languages. So shrubs is also called bushes in English, and then in French it's called arbuste and buisson, right? So what happens here is that the intended semantics of this relation is that apart from the fact that the term is a lexicalization of the concept, it's also important that these terms to each other are synonyms, or at least near synonymous. They need to mean the same thing. So the question now is, if we take some existing models and we look and we do a very basic check of some of their entities and labels, we can see already that the labels are not necessarily synonymous to each other. So, for instance, in KBpedia, which we will see more in later, there is the class profession, and it has as a labels occupation, which is correctly a synonym term for profession, vocation, work, and living. This is an interesting choice because you can say that okay, work might be, although it's a bit doubtful whether it always means a profession, but living definitely means something totally different, right? Living is not the same as a profession. Similarly, here in WordNet, we have the entity of Chief Executive Officer, and it has as label CEO, which is an acronym for Chief Executive Officer, so it's a correct label, it's a correct synonym. But we also have Chief Operating Officer, and I think most of you who work in the industry know very well that a Chief Operating Officer is not the same concept and not the same entity as a Chief Executive Officer. And you can see other examples as well, right? So the question is, why does this happen, right? Why we have these wrong synonyms, even though we know what labels are about, right? There are various reasons. The first reason is that we forget or ignore that synonym is a vague and context-dependent phenomenon. So some synonyms, some terms can be synonyms to each other in a particular context, but not in others, right? And if we don't explicitly say in which context they are synonyms, we end up with synonyms that for someone else are not really correct, are not really synonyms. A second thing is that we mix synonym with hyponymy and semantic relatedness in general. So if we go back here, for example, you will see that I think I don't have it as an example here, but Uh, I will show anyway. I will show this later, but we have the concept of relatedness. So, for example, indeed, a data scientist and a data engineer are related terms, but they are not the same thing. A data scientist and a research data scientist, actually, a research data scientist is a particular type of data scientist. So it's more a hyponym rather, right? Not all data scientists are research data scientists, right? But here, the way we represent this in this knowledge graph means the same thing. So every person that is identified as a research as a data scientist will also be identified as a research data scientist, which is something that we don't really, it's not correct actually, right? It's not correct. A third reason is that we are unaware of subtle but important differences in meaning for a particular domain or context, so we just may lack the domain expertise required. Sometimes we also need the term, but we don't want to create a new entity. And ultimately, it's that we don't document biases, assumptions, and choices. So it may be that we have a good reason why we put this together, but if this reason is not documented anywhere, it's really impossible to know just by looking at the data. So if there is no justification of why two seemingly non-synonyms are modeled as synonyms, right? Then we need to consider them as wrong. Okay, so now it's time for our first hands-on. So I'm going to demonstrate some very basic heuristics by which we can define, we can detect bad synonyms in a knowledge graph. Okay, so I'm going to open the Jupyter notebook. Okay. As I said, in order for you to follow this, please make a copy of the notebook and make sure that you have uploaded the the KBpedia knowledge graph N3 file. Okay, so let's start first with installing basic libraries that we will need. As I said earlier, we will need for this tutorial, for this hands-on, we will need sentence transformers, which is a deep learning model that allows to find semantic similarity between sentences. So if you haven't installed it, please start installing it. Then we will need RDF-lib. RDF-lib is a library that allows us to to access RDF graphs through Sparkle queries. Then we have Spacy. I'm going to use as a Spacy is an NLP library, and I'm going to download the English model. But generally, Spacy works for additional languages as well, and that's really useful. But today we're going to focus more on English. And yeah, let me see if this has finished. And after that, we're also going to install the OpenAI library in order to use GPT-3. As I'm installing this, is there any additional question? Okay, so a question by Michael. Could there be repercussions on downstream dependencies of an ontology if bad synonyms get removed? Any ideas of ways to design systems so they are more flexible to this relation changing? Actually, yes. It's a great question indeed. There can be repercussions because, as I said, first you might remove things that one repercussion is that the users who are used to seeing some things, they will not see it anymore, and that might not be what is desired, right? Uh, uh, which means that even though you are making your graph more correct, you are indeed harming the downstream application, right? So there are two situations here. If you're in a situation where you go to an existing knowledge graph and you you see this error, you see this problem, and you want to fix it, make sure you know all the dependencies. I know it's hard. This is where really, as a practitioner, you get crazy. But it's important that you don't just unilaterally change something without checking. Um, now, then what happens is that you may be in the second situation is when you design it from scratch, right? And the knowledge graph is not yet used. So there's a new application coming to use the knowledge graph. In that case, you need to make sure that with whoever team or system that they use synonyms as synonyms and not as other types of entities, because you may giving them labels, and if they expect something else, then they will definitely misuse it, right? So you need as a knowledge graph developer and governors in general to ensure that you are um, you are doing anything you can to make clear the application and the semantics, and monitor it, of course, right? You need to continuously monitor this and prevent things from happening in a proactive way. Okay, so we have installed now our software, and I'm going to just import some of the libraries. Okay, so everything goes well. So the first thing we need to do is to access the KBP knowledge graph. Now, in general, as I said, a knowledge graph can be very large, and we can access it in many ways, right? We can download a dump to and put it in some triple store or some other database and use an API, use Sparkle, things like that. Now, for KBP, the KBP is relatively small. It's around, I think, 40 megabytes. So what we're going to do is that we're just going to load it all in memory. So the code I have here just has a basic class entity, which has the ID and the name. ID is practically the URI of the entity because this is RDF. And a class called KBP the client, which when this class is created, it loads, as you can see here, the graph from the file. That's why I told you to add this file here. And then I have added two methods. One method retrieves from the knowledge graph the entities and their lexicalizations, and I use a Sparkle query to do that. And this method returns simply a dictionary whose keys are the URIs of the entities the and the values are lists of the different lexicalizations of this entity, the different labels in English, right? You can see the query here. I don't know what is your level of experience with Sparkle, but very briefly, what this says is that give me the entity URIs and the preferred and alternative labels that for entities that are not properties. So I deliberately did that. A second method that we're going to use for the second part of the second hands-on is to get the classes, right? So here we only care about the classes of the knowledge graph, and these are practically found by filtering them like that, so that the entity are of type all class. So let's execute this to be sure that the nodes, and now we just load the KBP knowledge graph in memory. So it should take not long, but let's see. So as we wait here, is there any question? Generally, I want to say that the way you are going to access the knowledge graph really can be different depending on the representation on the platform, right? So this is just an example here. You can also take KBpedia and just open the files, the M3, and parse them somewhere differently. It's not important, right? It's not the most critical thing. Okay, it's still running. Okay, great. So now, as we do that, let's also make a very basic Spacey setup. So what did I do here? I create the Spacey client. I initialized a model, the English model, and I created a very basic function that takes one sentence and tokenizes it. So it just returns the tokens. We will see why we need that. We need this for a particular heuristic that I'm going to use in order to detect problematic synonyms. But again, it's a very simple thing. I'm just using this to split any term, any compound term into multiple words, and I use deliberately space instead of something more naive in order to ensure that special cases like dashes or other things are taken into account. So you can execute this. And now we move on to start doing some detection. So what I'm going to do is that I'm going to load the entity lexicalization dictionary of Wikipedia using the method that I showed earlier. Well, we don't need that. And now I'm going to move to heuristics. So one first very simple heuristic to identify problematic lexicalization is a very simple count. So synonyms in general are rare, right? Real synonyms. For a given term, you may have two, three, five, I don't know, terms that are really synonyms. But if you see an entity having, I don't know, 50, 100 synonyms, lexicalization, then there's a high probability that they are not all synonyms. It's not always the case, right? It can happen, but it's rare. So what a very basic heuristic that I use here is that I'm taking the dictionary of entities lexicalizations and we're sorting it using as a criteria the number of lexicalizations. And then we print the first 100 items. So let's see what we get. Okay, now this is interesting. You see here, for example, what you see here, so what you see here is that this is the URI of the entity. And do you see that, for example, this entity here, which is has to do with some chemical substance, acetaminophen or something, has 182 labels in the same in English. I'm not an expert in this, but I'm pretty sure that all these are not synonyms to each other, not necessarily the same thing. But let's take a simpler example that we all know about, right? So let's take, for example, this one. Wikipedia.org Adventure Racing Sport. So this is most likely a class that is supposed to represent racing sports that are adventurous. You see in the labels that it has labels like adventure race, which okay makes sense, but it also have adventure events. An adventure event is not necessarily a racing sport, right? Because event is more generic than a sport, which means that this entity here, this lexicalization here, is not really a synonym of this. It's most likely a hypernym of the main entity. And you can see, and you can definitely find additional examples. So you can already see that with a very simple count query based on the intuition that real synonyms are rare, we can already identify quality issues. Now, let's move to a bit more complex, slightly more complex heuristic. This heuristic says that it's suspicious when the lexicalization of an entity starts or ends with the entity's name but is longer. For example, we may have the entity Python. Oh, sorry for that. We may have the entity with the name Python, and as a synonym, we also use Python programming language. This is legitimate, right? Because indeed, if the entity is about the Python programming language, this is another way, a bit more verbose way to represent that. But then we also have machine learning, and it may have lexicalization supervised machine learning. So the name is subset of the lexicalization. So you see that in the second case, the lexicalization actually denotes a more specific entity. Supervised machine learning is a type, is a narrower concept of machine learning. It's not equivalent to machine learning. So Using this heuristic, we can apply this heuristic with Spacey by tokenizing it and checking if the name of the entity is actually a part of the lexicalization, and try to identify those lexicalizations that just because they contain more words than the name, including the name of the entity, they are likely to be wrong synonyms. So when we run, let's run this and let's see what we get. So you can see that we already get quite interesting results, right? So you see, for example, that we have First Nation band number, which is a label of the entity. I will close this because I don't need more than that. Sorry, that First Nation number is potentially more specific in the collection. Dictionary of New Zealand biography. Well, this is more, but you can see many things, many cases here. Case of AIDS, all these types of entities. So you see that even though not all are problematic, this very simple heuristic identifies already wrong synonyms, right? And I only did this for 200 entities. You can, in theory, you can apply it to your whole set of entities. Now, a third heuristic is the inverse. A second heuristic is the inverse of this, is when the lexicalization of the entity is shorter than the name of the entity. So for example, we have the anti-Python programming language and we have as a shorter name Python, which is actually correct. But then we might also have supervised machine learning and its synonym is machine learning. So it's the other way around. So we use as a surface form, as a lexicalization, as a label, the smaller term. Again, sometimes this is correct, like here in the Python example. In other cases, it's not. So we can take the previous method and apply it inversely and see what's going on. And you can already see, again, very interesting examples. I'm just going to stop this. So, for instance, we have Instagram as a label for Instagram username. So the entity is about Instagram username, but it has a label Instagram. That's incorrect, right? Instagram is a more broader entity than Instagram username. Same for breed number, same for IMLSP. So again, you can see that simply based on this heuristic, we get already we detect systematic errors, because, and you can imagine that it's not just identifying one or two. If you remember what I talked earlier about trustworthiness, by just looking at this, I can now think, most likely whoever created this knowledge graph hasn't really taken well care of the synonymy problem, the synonym equality. So even though I haven't formally evaluated the accuracy of this model, I already don't trust it. At least I don't trust its synonyms to use it. A final heuristic for today for finding problematic synonyms is to try to see whether we have missing synonyms. That is, whether we have entities that are distinct, but they should actually be under the same entity. So terms that entities that are synonymous, but they aren't really modeled as synonymous. So what we're going to do here is that we're going to create a specific transformer model, pre-trained one, from SentenceBERT, the framework that I mentioned. Yeah, when we download it. And now what we're going to do is we're going to do something that this BERT is really good at. We're going to give it a number of entities, and we're going to ask it to create paraphrases. What this paraphrase does is that it does in a very efficient way. It calculates, given a list of terms, the pairs that have high similarity, and based on a threshold, we can actually print the pairs that have the highest similarity. And I'm going to use here a very high threshold, 0.9, and see what happens. So it takes a couple of seconds to work. Of course, this particular method here, if you apply it in hundreds of thousands of names, it may be, of course, slower. But for now, this runs quite fast. Okay, and you can already see that we are getting pairs that have scored a very high level of similarity. If you check this, you will see that in most of the cases, these are actually non-synonyms that are correctly distinct entities. Therefore, yeah, we haven't really found any big problems. But on the other hand, it's interesting to see some of the cases that at least require some further check. So, for example, we see an African bean and an Africanized bee. Are these really different, or perhaps they should be under the same entity? Is accelerating an accelerator also different enough to merit distinct representation of entities, or again, they should be labels of the same entity, right? So this method can be applied not only with sentence verb, but can be applied with generally any embedding based model for similarity. You can even use string similarity if you want, right? And but it's very handy and it's very fast. It very fast can tell you whether you have non-identified duplicates in your knowledge graph. Okay, I will stop this part here. Let me know if you have any questions so far. So to summarize, as I'm waiting for questions, so we saw that we used some very basic, so we used three, let's say, groups of heuristics here. One was a basic count. The intuition is that synonyms are rare, therefore entities with many lexicalizations are suspicious. Second, second, some very basic syntactic hypernym, if you like, that also is suspicious. And finally, some embedding-based semantic similarity that also identifies duplicates. Okay, let's move on. We have with the presentation. Okay, let's go now to problematic classes. Okay, so in the terminology of semantic models and knowledge graphs, the difference between class and individuals is that classes are abstract entities that represent kinds of things in the world that may serve as semantic types of other entities, concrete or abstract. And the entities that belong to a class are also known as instances or individuals. So, for example, we have the class building, and an instance of that class would be the Empire State Building. We have the class dog, and an instance of it would be a particular dog, like Lassie. And we could have the class computer, and a particular lap. For example, my computer here, my laptop would be a particular instance of it. And this distinction between classes and individuals is very common in RDF and all models and knowledge graphs. Now, I would like you to take a look in this ontology here. In this, actually, this is a subclass taxonomy, class taxonomy from SNOMED, from the SNOMED ontology. So all this, what you see here are classes, and the relation between these is superclass. Can you detect any problem here? I'll give you 1 minute to tell me if you see any problem with respect to the subclass relation in these models. Please write it in chat if you have any idea what's happening. Alex, instances as classes. Exactly. Exactly. So one first example, right, great. Countries aren't classes. That's the first thing that you can see here, right? Countries are not classes. And it's um, it's a typical problem that we find many times in ontologies and knowledge graphs, individual entities modeled as classes. There are several reasons, we will see those, but that's one thing. Then, a second is this one. We have secretary, which looks like a legitimate class. And the thing is that secretary is a class, and we can see that now, look at this problem. A secretary, is it a subclass of occupation or a particular instance of occupation? A secretary on its own indeed can be a class, because a person that works as a secretary can be identified, can be an instance of that class. But look at the paradox here. If, let's say, Panos becomes an instance of secretary, let's say I'm a secretary, then by means of reasoning, I'm also an occupation. Because the rule for subclasses is that every instance of a class is also an instance of the superclass. So really what has happened here is that this here is not, it's a class, but the relation to this class is not a subclass relation, right? It's still an instance relation. So what's going on here? There is this so-called concept equals class fallacy. In all other frameworks, many times the term concept is used interchangeably with the term class. And this is only partially correct. A concept can play the role of a class if its definition implies a set of entities that instantiate it. But this is not always the case. The only criterion that matters when determining if an abstract entity can be a class is whether there are other entities that can be instances of it. In that sense, a country can never be a class. An individual person can never be a class, right? And also, a subclass hierarchy is not equivalent to a broader, narrower hierarchy. And as we saw with the case of secretary, it can be that an entity can be both a class and an individual, depending on how you view it. For example, the entity eagle can be modeled as a class, representing the set of all individual eagles on Earth, and it can also be modeled as an individual, belonging to the class animal species. What happens is that certain variations of OL, especially OL light and OL DL, do not allow an entity to be both a class and an individual. And because that happens, many knowledge engineers are conditioned that we cannot have meta classes in an ontology, and therefore I need to model everything as a subclass relation. So generally, the reason we define bad subclasses is that the easy expression itself is ambiguity, right? Because, of course, for example, Greece is a country, and but also Greece is a European country, and European country is a country. Second order classes are not allowed, and we have assuming the subclass hierarchies are the same as narrow broader, or the constant equals class fallacy. So, for my second hands-on here, I'm going to go back now to the notebook, and we'll continue to see one nice, interesting way to detect some problematic classes. Here we are. Sorry for that. Okay. As I said, I'm going to use GPT-3. So GPT-3, I'm using the paid API version of my own. So here I have, I just put the key here. I trust that you're not going to abuse it, but also after this masterclass, I'm going to delete it. So if you want to continue using this code, please make sure that you have an API key. By the way, this is for GPT-3, it's not for GPT-4 or ChatGPT, right? It's an older model, but it will fit for our purposes. So let's initialize this, and let's load the classes now of KBpedia. So I don't know if you already know how GPT and this kind of models work. So these are in general generative models, meaning that you give it a prompt, you give it an instruction, and then the model tries to complete the text of that prompt, right? So the way we're going to use it is practically by asking, we're going to treat GPT-3 as a domain expert, and we're going to pose it questions. The first question I want to pose to GPT-3 is if a given class, simply based on its name, it refers to a single person, location, organization, or geopolitical entity. That is, if it is a named entity, because if it's a particular location, person, organization, it shouldn't be a class. So I created a very basic API call of GPT-3. We define the prompt. It's important. I'm not an expert in prompt engineering. You can find many interesting resources about this. But for now, what I said is that just tell me if this term refers to a single person, location, organization, or geopolitical entity. And please answer me with just a yes or no. I'm using the GPT-3 engine, the most advanced one for GPT-3 at least, which is DaVinci 03. And I put a temperature of 0. The temperature, just to know, is a metric, is a parameter that adjusts the creativity of the model. The lower it is, the more consistent is the model in its answers. For the same input, for the same prompt, it will identify, it will return you the most probable answer. If temperature is higher, then it will try to be more creative, and every time it will try to be more diverse and give you more results. Because this is a classification task, we want the temperature to be 0, to be as low as possible. So by using this simple method, then we can take the classes that we just identified and give the name of the class as input and print those classes that are identified by GPT-3 as named entities, as persons, locations, etc. Of course, GPT-3 will not be perfect, right? It will have all positive. It's still a classifier in that sense. I'm afraid I cannot use it at the moment. Sorry for that because of the rate. Let's see if we have. I'll try again. No, I exceeded my rate limit for today. Sorry for that. But what you would see here, and I urge you to run this with your own GPT-3, is that you will see that many KBPDA contains a lot of entities that are either persons, organizations, or locations, and are identified as classes instead of individual entities. Right? Okay. A second heuristic that I have here, and again, because of the rate limit, I'm afraid I won't be able to use it, is about vagueness, right? Remember the vagueness that I mentioned. So it's not fully problematic to have vague classes, but the thing is that when you have a vague class, it's important that you know it's vague, and we should know that it's vague, and we should expect that we know that it's vague, and we should expect that it might cause problems, which means that we need to define it in as crisp way as possible. So for this task, I also use GPT-3 as a domain expert, or not domain as an expert of what vagueness is, but I'm helping it a bit. So what I'm doing is that I'm giving as a prompt a definition of vagueness for a predicate, right? And I'm giving some examples. I'm telling you, for example, that tall is vague. Why? Because of that. And again, I ask it, is this term vague? Tell me a yes or no. And then I take the class names and I pass them from GPT-3. I'm not sure if it's going to work now, but it should, if it works, it should print those class names that GPT-3 believes are vague. One way to make this even smarter, let's say, to help GPT further, would be for its class name to give it as input also the definition that it may have. Yeah, so this doesn't work, but you can get my point, right? So again, it's a very convenient and fast way to detect some of the potential problems that we may have. So I will stop sharing here. And we still have 10 minutes, so I think I'm going to start wrapping up and then start the Q&A. So Share screen. Okay, so I hope that from this masterclass, apart from some uh, practical knowledge, you have gotten three takeaways. The first is that shared meaning is important in knowledge graph, right? Meaning accuracy, explicit, and agreement are important aspects for good quality knowledge graphs. And all these three factors, these three dimensions, right, are usually not perfect and not followed because there are several elements, as they like to call them. There's ambiguity, there's variety, there's vagueness, there's semantic change, so yeah, semantic modeling stuff. But there are also bad practices, right? We've seen we can start facing them by better quality management. And quality management means that we need to be aware of the main quality dimensions and problem causes. That was the first part of the masterclass. To understand and avoid key quality pitfalls, and to understand and draw your own strategies for quality dilemmas and trade-offs. And this kind of methods that I showed, I hope that at least have helped you a bit to kickstart or to enhance your already existing knowledge graph quality practices. So before I take the Q&A, I would like to let you know that this masterclass today is a part of a broader bootcamp that I'm going to deliver in July with O'Reilly. It's going to be a 3 hour live sessions covering the complete life cycle of knowledge graph development, starting from specification, schema design, population methods, and quality assessment. So you are all welcome to join on that. So yeah, thank you very much for listening to me, and I'm open to questions. We have around 8 minutes. Yeah. Nick, as I said, I wanted the reason I showed GPTs is because it can be quite fast way to detect some things. It will definitely have false positives, and you will definitely need further prompt engineering, or at least to see what works and what not. Right? It's a bit of it's still very speculative. I wouldn't trust it also fully in production, but for quality purposes, to just try and identify things that are definitely wrong, it can really help without needing to create something very, without needing to train your own, not even your own model, as you can see, right? So in frequencies like this, Zaire with capital or not, and generally keep in mind that all the language models, the large language models, work better the more context you give. So if you say that I have Zaire, and to give it some further context about where you find Zaire, then indeed it might help. For instance, if Zaire, let's say, is modeled as a subclass of country, and you give that as information, then maybe it find it, right? Did I try my method to check the synonym to align different ontologies? Okay, yes. So I have used this. By the way, you can see in the screen, so before I answer the question, you can see in the screen there is a link to a survey. Please take a moment to fill it in, to give feedback both for this session and generally for your experience. So the question about this, yes, indeed, it can be used to align different ontologies. I'm not sure whether how easy is for GPT to work. Definitely embeddings can help to try and find associations. We are actually using it. We're using the embeddings for every time we want the embedding based method. We use it in my company, in my team. Every time we have new terminology that we want to add in a graph, and we want to decide whether a new term needs to become to be incorporated in an existing entity, if it's a synonym already, or if it has to become a new concept, a new entity. Unfortunately, synonym detection automatic synonym detection is not very precise. I haven't seen any synonym detector with more than 60-70% precision. So you need a human in the loop there, typically. For synonyms. For relatedness, it's okay. Okay, Angela, about non-English ontology and how well these heuristics work for that. Okay, so the first heuristic about the number of entities, right? It's language independent. You can have a look on that. The things that I showed with Spacey, it really so Spacey and can perform tokenization in additional languages. Now, some of the heuristics will like the ones with the substring will probably not work easily. For example, for German, right? Because German tends to concatenate the words. So it really depends on that. It really depends on your target language. And I don't know whether it would work in Japanese or in other languages that I don't know. I would say that what I showed with the Spacey heuristics, I would say for Greek, for French, for this kind of European language, most likely work. But again, it's I cannot know a priori. Then in the embeddings based methods or GPT-3, etc., also have to do with how well with how well these models have been trained on data of this language. And in theory, they can also be used to find associations and alignments and problematic alignments between across languages, hopefully. There's a question says, instead of checking synonyms, can you create a list of accurate synonyms? Yes, I mean, that's the thing. In theory, if you build your model, your goal is to create a list of accurate synonyms. But what happens is that most of the cases you cannot control that, or you don't have enough time to do that. So sometimes you utilize a method and you do a post quality analysis. Sometimes you need to add some noise in your to allow some noise in your model just because you don't have enough time to properly curate it. Vice versa, not vice versa, and also like in this masterclass here, sometimes you need to use an existing model that someone else has built. Else meaning an organization, some maybe open source. In that case, you need to check if it has synonyms. Okay, let me see if I can see some questions here. What are the top 2 to 5 ontology modeling tools that you might recommend? I don't have particular recommendation, but one clarification here. What do we mean by modeling? If you are talking about tools that allow you to about schema design, like Protege, for example, yeah, again, I don't have a favorite. In at TextKernel, we don't use RDF. We use property graphs. We use Neo4j. So we have an in-house editor for that. It really depends on what kind of technology you use. So I don't have a good answer for that. Okay, there's a nice question here. Since this is an example of a nuance that could vary by culture, is there any way that someone could provide this context within the data rather than having a separate document explaining all these nuances? Yes. So you can either do it within the data, within the knowledge graph. You can either add any assumptions, any biases, any nuances as documentation, so as annotation properties or as definitions, etc. Or even depending on how much you want to do it on with contextualization properties. So for example, you can have a relation of synonymy and say that this is synonym only under this particular conditions and context. The context can be location. There are some ontologies and some formal models for representing context. I don't have any particular recommendation in mind. But I would say that, of course, ideally you want to do that, but even making a very basic documentation at the definition level, it's already good. It can go a long way, let's say, on increasing the quality and the trustworthiness of your model. Because keep in mind that, for me at least, a trustworthy model is not only a model that is good; it's also a model that admits its mistakes and its limitations. The same way how the same should happen in machine learning, I guess, and in general in AI. Okay, our time is up. I will stay online for, I don't know, for another 5 to 10 minutes if you want. If you have still have for questions. If you have any further questions in general that I haven't addressed here, feel free to contact me. Connect with me in LinkedIn, follow me on Twitter, and generally, or just send me an email. But I'm still taking questions, so please feel free. Let me check here. Sorry, I lost my connection. Okay, how can we attend your tutorial in June or July? So it's the tutorial is available through the O'Reilly Learning platform, and the O'Reilly Learning platform is subscription based. So you can subscribe per year, and it includes access to all the books and all the live trainings. And there is also for newcomers, there is also a trial period for 10 days. So uh, my two sessions will be with a week apart, so you can also join a trial, make a trial version, a trial a trial membership, and you should be able to access it. Actually, this is I'm writing down here. Then, if you want to know more, send me an email, and I will give you more concrete information on that. So, where do we get the notebook again? In the beginning of the chat, I have a link to a Google Drive that contains the slides, the notebook, and the Wikipedia data. So you should be able to access it. Again, if you are missing either anything, just send me an email, and I will make sure to send you the material. Yeah, and you can see it actually pinned it now in the chat box by our host. So thank you very much. Okay, so again, thank you all for joining. I wish you a good day or evening, depending on your time zone, and enjoy the rest of the conference. And again, feel free to contact me for anything you might need, you might want or need. So, bye.